The objective of this lecture is to provide several examples demonstrating the application of Euler's laws to rigid body kinetics problems. The first example is the following problem. Consider an inertially fixed shaft upon which a particle, which is in the form of a collar, slides. Now, attached to the collar, so the collar is going to be denoted point Q, attached to the collar is a slender uniform rod or slender uniform arm of mass m and length L. The center of mass of the arm is at point C. The displacement of point Q relative to the ground or relative to the shaft will be denoted y, and the angle formed by the vertically downward direction and the arm is going to be denoted theta, and gravity acts downward. Now actually, to be completely precise here, the mass of the collar is going to be denoted m1, the mass of the arm is going to be denoted m2, and its length is going to be L. The goal is to determine the differential equations of motion. Determine the differential equations that describe the motion of the collar arm system. Now, it's really important, and this is something that is really critical in doing rigid body mechanics problems, is that I'm going to put this note right at the beginning so that we have it set up right from the get-go so that we're not debating it later, is that the strong form of Newton's third law does not apply to a rigid body. It applies to a particle or a system of particles, but does not apply to a rigid body. Now, because of that, we have to be very careful when we draw the free body diagrams for these objects. But let's go through and let's do the kinematics. So in this particular case, because we're dealing with a particle and a rigid body, we can actually draw two separate free body diagrams because we don't have to worry about this force of interaction between the two satisfying the strong form of Newton's third law. So the first thing we'll do is we'll do the kinematics. So they're going to be two reference frames. So there's one rotation and one translation in this problem. So there's one rotation, so that makes two frames. So that implies two reference frames. And I'm going to put down these two frames as follows, which is that the first reference frame is going to be the ground, or going to be the inertial frame, and the second frame is going to be the arm, which is also the body. So because I denote oftentimes the body as B, we'll say B is the arm. Now, the coordinate system that's going to be fixed to the ground, its origin, is going to be at Q when x equals 0. That's an inertially fixed point. Then I'm going to put EX is going to be along QC when theta equals 0. And then EZ is going to be out of the page. And then EY is going to equal EZ crossed with EX. The coordinate system that's fixed to the arm is going to have its origin at Q. Then ER is going to be along QC. EZ is going to equal big EZ. And then E theta is going to equal EZ crossed with ER. So now if you look, you'll see that these coordinate systems are as follows. base E is actually EX, EY, EZ is out of the page, and then I have ER, and then E theta, and then E little ez is equal to big Ez. The angle here is theta. So given the way I define the coordinate systems, you can see that the position of Q has to be measured from where Q is when x equals 0, which I'll just denote as the position of Q because it's just easier that way. And that equals y, Ey, which gives that the velocity of point Q in the ground is y dot Ey, and the acceleration of point Q as viewed by an observer fixed to the ground is y double dot Ey. The next thing I need, because that's all I need for the collar, because the collar is a particle, so there's only one law of mechanics that's going to be applied to the collar. But for the arm, I need to get two pieces of kinematic information. First, I need the acceleration of the center of mass. So C is the center of mass of the arm. And you can see that as a result, I have to measure point C from where Q was when x equals 0, because that is the inertially fixed point. So this is equal to the position of Q relative to where Q was when x equals 0, and then plus the position of C relative to Q. So that's equal to it's equal to y Ey plus L over 2 ER, because the center of mass of the arm is a distance L over 2 from the point Q. So as a result of that, now we can compute the velocity of the center of mass. So this is V bar G, and notice that this also is equal to, for completeness, this is R bar. This is equal to y dot Ey, and then we have to say plus the rate of change in the ground of the position of C relative to Q, but that's equal to y dot Ey plus the rate of change in the body of the position of C relative to Q plus the angular velocity of the body in the ground crossed with RC relative to Q, which gives y dot Ey plus theta dot Ez crossed with L over 2 ER, which gives y dot Ey plus L theta dot over 2 E theta. So that's the velocity of the center of mass. Now we need the acceleration of the center of mass. So the acceleration of C in G is equal to A bar G, which is equal to, well, y double dot Ey, that's the first part. And then I've got plus d dt in G of the velocity of the center of mass in G. That's equal to y double dot Ey. And then I've got plus d dt in B of the velocity of the center of mass in G plus the angular velocity of B in G crossed with V bar G, which is equal to y double dot Ey. And then I have plus L theta double dot over 2 E theta plus theta dot Ez crossed with L theta dot over 2 E theta, which is equal to y double dot Ey minus L theta dot squared over 2 ER plus L theta double dot over 2 E theta, where I flipped the order of the last two terms after I took the cross product. So that's the acceleration of the center of mass. Next, we need the angular momentum of the arm relative to its center of mass. This is equal to the moment of inertia tensor of the body multiplied by the angular velocity of the body in the inertial frame. Now, because this coordinate system, ER, E theta, EZ, remember, this is fixed in the inertial frame, and this is fixed in the body. And ER, E theta, EZ is a principal axis coordinate system. So because, let's say, let E equal ER, E theta, EZ, and together with the center of mass, so together with C, which is the center of mass of the arm, the system C, ER, I'll just denote it this way, C, and then E is a principal axis coordinate system from which we can actually write that the inertia tensor, if I write this in tensor form, it's equal to IR bar ER circle cross ER plus I theta bar E theta circle cross E theta plus IZ bar EZ circle cross EZ. But remember, we generally write this in its matrix representation. So when we write this in its matrix representation, this becomes a diagonal matrix IR bar, I theta bar, IZ bar, and then all zeros. And remember that the angular velocity of the body in the ground, when that's expressed in this basis E, that's equal to 0, 0, and theta dot. So as a result, when we multiply the two, the angular momentum relative to the center of mass expressed in this basis E is equal to the inertia tensor of the body expressed in the basis E multiplied by the angular velocity of the body in the ground expressed in this basis E, which is equal to, when we get through doing these calculations, we get 0, 0, IZ bar theta dot. But IZ bar for an arm, this is equal to ml squared over 12. So as a result, the angular momentum relative to the center of mass is equal to ml squared over 12 theta dot EZ. So there we go, for a uniform slender arm using a principal axis coordinate system. And from this, we can actually compute the rate of change of the angular momentum. So the rate of change in the ground of the angular momentum relative to the center of mass, because the direction EZ is inertially fixed, we know that the rate of change of the angular momentum is ml squared over 12 theta double dot EZ. Now, let's apply the laws of mechanics. So Euler's laws. Remember that the first one is that the force is equal to the mass times the acceleration of the center of mass relative to an inertial frame. The second one is that the moment is equal to the rate of change in the inertial frame of the angular momentum relative to the inertial frame. Notice that both of the right-hand sides we have A bar and d dt in G of H bar G. So now what we're going to do is this is for, remember that we have a particle and we have a rigid body. So this is for the arm. And then we have Newton's second law. And this is for the collar. So what this says is that the force applied to the collar is equal to the mass of the collar times the acceleration of the collar in the inertial frame. So let's draw the free body diagram. So here's the free body diagram of the collar. This has the following free body diagram. We have M1G. We have a normal force due to the track. And then we have a reaction force, R. Now, if I do the same thing for the arm, so let's draw it over here, free body diagram. In this case, it's the arm. So the forces acting on the arm, we have negative R, and then here's the arm. And then we have M2G acting at the center of mass of the arm. Now, this is where the strong form of Newton's third law does not apply. R does not lie along the axis of the arm. So in which case we actually have to write it a little differently from the way we would otherwise write it. So we have to write all these forces out. So let's write all the forces out first. We've got m1g is equal to m1g times ex. We have m2g is equal to m2g times ex. We also have that n lies in the direction of ex. But the last force is the one that we have to be careful about. R actually lies in the direction of it's got two components. It's got an ER component and an E theta component because it doesn't lie along the ER direction because ER is along the arm, and I said it doesn't lie along the axis of the arm because it doesn't satisfy the strong form of Newton's third law. So now let's do these together. So we know for the collar, again, we have Newton's second law. So we've got FQ equals M1 AQ in G. Well, FQ is equal to what? It's equal to M1G plus N plus R, which is equal to M1G EX plus N EX plus R sub R ER plus R sub theta E sub theta. And that has to equal M1 X double dot EX. So from this, we actually get two equations. If we look at this, it's easiest to take the dot products in the EX and the EY directions just because the acceleration in this case is in the EX direction. So if we take FQ and we dot it with EX, we get, this is M1 Y double dot EY. If we go back over here, you'll actually see that yes, it's the acceleration of Q. So I forgot that I put Y in the horizontal direction. So in this case, we get, if we take FQ dotted with EX, we get M1G plus N, and then we get plus R sub R ER dotted with EX plus R sub theta E theta dotted with EX, and that has to equal 0. So there's no component of acceleration in that direction. If I take FQ and I dot it with EY, we get R sub R ER dotted with EY plus R sub theta E theta dotted with EY, and that has to equal M1 Y double dot. So now what we can do is we can look back at the picture and we can see this. We see that ER is equal to cosine of theta EX plus the sine of theta times EY, and E theta is equal to, if you go back over to the picture, you'll see that E theta is equal to minus the sine of theta times EX plus the cosine of theta times EY. So it's minus the sine of theta EX plus the cosine of theta times EY. So now we have to take a few dot products. So if we take ER dotted with EX, so ER dotted with EX is equal to cosine of theta. And then we have the next one is E theta dotted with EX is equal to minus the sine of theta. The next one we have ER dotted with EY is equal to sine of theta. And then we have the last one is E theta dotted with EY. And that's equal to cosine of theta. So as a result, these first two equations that we get when we finally put them in scalar form, look as follows. We've got M1G plus N, and then we have plus R sub R ER dotted with EX, so that's plus R sub R cosine of theta, and then we have plus R sub theta, and then E theta dotted with EX, which gives us, which flips the sign, and we get minus r sub theta times the sine of theta, and that has to equal 0. The second equation gives us r sub r, and then we've got e theta dotted with ey, e theta dotted with, er dotted with ey, er dotted with ey is sine theta, so we get r sub r sine theta, and then we've got e theta dotted with ey times r sub theta. E theta dotted with ey is cosine theta, so we get plus r sub theta cosine theta, and that has to equal m1y double dot. So that's the first two equations. Now you'll notice that there are unknown reaction forces in all these equations. So these two together give us two equations. So let's write this down. Two equations and three unknowns. So we don't have enough equations, which we shouldn't because we haven't analyzed the arm yet. So now let's go on to the arm. So for the arm, we have to do the following. Notice for the collar, we applied Newton's second law. So for the arm, we're going to apply F equals ma bar g, and then we're going to apply m bar equals d dt in g of h bar g. So F applied to the arm now. So if you go back to the free body diagram of the arm, you'll see that there are two forces, negative r and m2g, right? M2g. So this gives us negative r plus m2g. And that has to equal negative r sub r er minus r sub theta e theta plus m2g ex. And that equals the mass of the arm times the acceleration of the center of mass of the arm. Okay. Now, if you break this down, the easiest components in which to break this down are the ER and the E theta components. So if I take F dotted with ER, what we get is we get minus R sub R, and we get plus M2G EX dotted with ER, and that has to equal M2 Y double dot EY dotted with ER, and then minus m2l theta dot squared over 2, and that's it, because the second term has an e theta component in it, so that one's gone. Or sorry, the third term, and the only one that survives is the second one. Now we can do ex dotted with er, and if we go back over here, we can see that er, if we dot it with ex, that gives us cosine of theta. So then the third equation that we get is we get minus r sub r plus m2g times the cosine of theta equals, and then we have ey dotted with er, which gives us sine of theta, so we get m2 y double dot times the sine of theta minus m2l theta dot squared over 2. So that gives us an expression for r sub r. That's the third equation. The fourth equation, we've got f dotted with e theta is equal to, well, now we've got minus r sub theta, and we've got plus m2g ex dotted with e theta, and that has to equal m2 y double dot ey dotted with e theta, and then plus m2l theta double dot over 2. Now the second term actually disappears because we're dotting with e theta. So that gives us the fourth equation. The fourth equation is minus r sub theta, and then plus m2g, and ex dotted with e theta. So we take e theta and ex, we get minus the sine of theta. Okay. And then that has to equal m2 y double dot ey dotted with e theta. So if I take e theta and I dot it with ey, I get cosine theta. So this gives me, this equals m2 y double dot cosine of theta. And then I have plus m2 l theta double dot, all divided by 2. So that takes care of the two equations that come out of Euler's first law. Second, the last one is we need to compute the moment relative to the center of mass to apply Euler's second law. And if we actually look, we see that the moment is equal to, it's equal to RQ minus R bar crossed with minus R. It's because the gravity force goes through the center of mass. So this is equal to minus L over 2 ER crossed with minus R sub R ER minus R sub theta E theta, which is equal to, and we've got L R sub theta all divided by 2, and then we've got EZ, and that has to equal the rate of change in the inertial frame of the angular momentum relative to the center of mass, which is equal to ml squared over 12 theta double dot EZ, from which we obtain the fifth equation, which is L R sub theta over 2 is equal to ml squared over 12 theta double dot. So now we have 5 equations. Now let's look at all 5 of these equations. Remember, we had 2 equations and 3 unknowns. We've added now for 3 and 4. So 3 plus 4 give plus 2 equations and plus 0 unknowns, meaning that we've added 2 equations, but we haven't added any unknowns, right? And then 5, if we add to that, we get plus 1 equation and plus 0 unknowns. So the total, when we're all done, is 5 equations and 3 unknowns. So now we can start simplifying. So let's figure out how to do that. So from 5, what do we get? We get that R sub theta is equal to m2L over 6 theta double dot. And actually, to be careful about this, this is m2. So I just want to go back and make sure that we put a 2 on this. This is m2L squared over 12 theta double dot. And that makes this m2L squared over 12 theta double dot. So now we can solve for R sub theta, and we get m2L over 6 theta double dot. Now what we can do is we can take that and we can start substituting in to these different equations. If you look at 4, I can now substitute in for 4, and I can get one of the differential equations because I've got R sub theta. R sub theta is m2L over 6 theta double dot. So I put it in to number 4, and I get minus m2L over 6 theta double dot. That's minus R sub theta, minus m2g times the sine of theta, and that equals m2y double dot cosine theta, and then plus m2 L theta double dot over 2. Now that's one of the differential equations because there are no unknowns in there, right? So that's the first one. So now we've exhausted that. So now we have to go back and look at the other equations, and you'll see that equation 3 has an R sub R in it. And then if I look at equations 1 and 2, you'll see that there's an R sub R and an R sub theta in each one of them. So what I can do is I can take equation 3 and I can solve for R sub R. So if I take equation 3 and solve for R sub R, what do I get? So solving 3 for R sub R gives us the following. Well, I need to move R sub R to the other side. So I get R sub R is equal to m2g times the cosine of theta, and then I get minus m2y double dot sine of theta, and then I get plus m2l theta dot squared over 2. So that's R sub R. Now what I can do is I can take that component of that reaction force and I can put both of those into equation 2. So I can substitute R sub R and R sub theta. So substitute R sub R and R sub theta into 2. And when I do that, what do we get? We've got R sub R times the sine of theta. So R sub R is m2g sine theta minus m2 y double dot sine theta plus m2L theta dot squared over 2, the whole thing, times the sine of theta, and then plus r sub theta, but r sub theta, we already have r sub theta from there, plus m2L over 6 theta double dot times the cosine of theta, and that has to equal m2, let's see here, m1 y double dot. m1 y double dot. So that is the second differential equation. And you can see that there's nothing in there that's unknown. So here's the first differential equation, and here's the second differential equation. And so we're done with this example. That's how you solve and get through this example. Now we're going to do another problem. The next problem that we're going to do is going to be the following example. So in this problem, we have an inclined plane, and on the inclined plane we have a sphere, and this sphere has mass m and radius r, and it's being pushed by a piston up the incline. So the force that's being applied by the piston is this force P. So this is a piston, if you want to, or a plate, either one is fine. The center of mass of the sphere is going to be located at C, and the displacement of C up the incline is x. Now, there's a friction force that acts right here between the piston and the sphere. So this is Coulomb friction, and it has a Coulomb friction coefficient mu. There's no slip at this point of contact here, which I'm going to call Q. And the angle formed by the horizontal with the incline, that's beta, and this incline is inertially fixed. It's the ground. And then there's gravity acting down. So the goal is, as always, is to determine the differential equation. Determine the differential equation of motion for the sphere. Now, in this particular case, we have to be really careful because we have to apply the laws of mechanics, but we have to get a lot of information in order to do this because I did not give you an angle in this case. I gave you a displacement x. So we know that the force applied to the sphere is equal to the mass times the acceleration of the center of mass of the sphere. We also know that the moment is equal to the rate of change in the ground of the angular momentum relative to the ground. So now we have to get all this information. So in this case, we're going to have two coordinate systems, and I'm going to draw the two coordinate systems using a bigger version of the sphere. The first coordinate system is going to describe the position of point C, right? So C was somewhere when x equals 0, and this displacement up the incline is this distance that this thing has gone since it started. So that's x. So I'm going to put ex along or up the incline. I'm going to put ey such that with ez being into the page, ey is equal to the cross product of ez with ex. The next coordinate system is going to be fixed to the body, and it's going to have one of its basis vectors. It doesn't matter really what I call this. And actually, just to make this a little clearer, maybe I'll do it this way. Maybe what I'll do is instead of calling this with little e's, I'll call this big EX, I'll call this big EZ, and I'll call this big EY. Because then I can call these little EX, and I can call this little EZ, and then the cross product is little EY. Now it's very important to understand that this basis is fixed in the ground, while this one over here is fixed in the body. Okay, so now in order to do this, we have to get all of these quantities here, the acceleration of the center of mass. So now I know that the position of the center of mass, which is also equal to the position of C relative to where c was when x equals 0 is equal to x ex, which says that the velocity is equal to x dot ex, which says that the acceleration is equal to x double dot ex. So that gives me the acceleration of the center of mass of the sphere. The next thing I need is the angular momentum relative to the center of mass. This is equal to the moment of inertia tensor of the body multiplied by the angular velocity of the body in the inertial frame. Now, in this particular case, we're going to say let E equal Ex, Ey, Ez. So now, C together with this basis E is a principal axis coordinate system. So as a result of it being a principal axis coordinate system, I know that the inertia tensor of the body, when expressed in this basis E relative to the center of mass, is going to equal Ix bar, Iy bar, Iz bar, with all zeros elsewhere. Okay, but I haven't gotten the angular velocity of the body yet. So, because notice that I gave you, so in this problem, we were given a displacement and there's a no slip condition. So I have to get this angular velocity first before I can actually finish this angular momentum. I haven't needed it yet because I've been dealing with translational motion, but now I'm going to be dealing with rotational motion. So note that the angular velocity of the body in the ground has a general form of omega Ez because it's into the page. And we also have to note the following thing, which is the no-slip condition says that the velocity of the point of contact on the body in the ground has to equal the velocity of the point of contact on the ground in the ground. And that is equal to 0 because the point on the ground is inertially fixed, which makes this equal to 0. This together, this whole thing is the no-slip condition, right? This is no slip. So as a result, the velocity of point Q on the ground has to equal 0, which tells me now how to compute the velocity of the center of mass. The velocity of point C, which is the velocity of the center of mass, is equal to the velocity of point Q plus the angular velocity of the body in the ground crossed with RC minus RQ. But the velocity of point Q is 0 because of the no-slip condition, and this is omega Ez crossed with minus R E Y, the way I have it configured, right? Because the radius of this sphere, probably didn't label it, the radius of the sphere is R. So as a result, this tells me that the velocity of point C is equal to, well, Ez crossed with Ey is minus Ex, so I get R omega Ex. But I already know that that has to equal X dot Ex, because from earlier, I got that the velocity of the center of mass is X dot Ex. Now I can solve for omega, which tells me that omega is equal to X dot over R. So that tells me that the angular momentum now, which is equal to this inertia tensor. Now I can go back to the inertia tensor, right? I know that when I express this angular momentum in this basis E, it's equal to the inertia tensor expressed in the basis E multiplied by the angular velocity of the body in the ground expressed in the basis E. But the angular velocity of the body in the ground expressed in the basis E is equal to 0, 0 omega, which is equal to 0, 0 x dot over r. So this tells me that the angular momentum relative to the center of mass, when I get through multiplying this out, gives me Iz bar times x dot over r times Ez. But Iz bar for a sphere, since it's a principal axis coordinate system, is equal to 2/5 mr squared, which says that the angular momentum relative to the center of mass is equal to 2/5 mr x dot Ez. So that tells me, because Ez is inertially fixed, it tells me that the rate of change in the inertial frame of the angular momentum relative to the center of mass is 2/5 mr x double dot ez. So look what I've done so far, is I started off back here where I needed the acceleration. I'm going to apply Euler's two laws. I need the acceleration of the center of mass and the rate of change of the angular momentum relative to the center of mass. I now have everything on the right-hand side. So now I can draw the free body diagram. So if I draw the free body diagram of the sphere, here's what it looks like. And this is where things get a little bit complicated because you have to be careful as to how you figure out these forces. Okay, so this force, there's a normal force here. There's a rolling force. I'm going to call this force F sub r, which is the rolling force, which is also a static friction force. I now have three other forces. I've got the force of gravity, which acts at the center of mass. And then I also have a force P, which acts here, which is given. And then I have a Coulomb friction force, which acts here. I have to figure all these out. Some of these are a little bit simpler than others, but we'll do them one at a time. We know that N is equal to NEY. We know that F sub r is equal to F sub r times EX. We also know that P is equal to P times EX. Those three are pretty straightforward. But the force of gravity, we have to do a little bit of work to get it. It's in the unit vertical downward. And we know that the friction force, because it's a dynamic Coulomb friction force, is minus mu times the magnitude of the normal force. The normal force in this case is P, because the force that's acting at that point is P. So it's the magnitude of P times the velocity of that point, this point right here. Let's call this point, for simplicity, let's call it A. So the velocity of A, as viewed by an observer fixed to the piston, divided by the magnitude of the velocity of A as viewed by an observer fixed to the piston. And I'm going to call P equal to the piston, which is the thing that's pushing the boulder up the incline. Okay, so now if we try to get this, now we have to figure out the velocity of point A, and we got to get this unit vertical downward. So let's get the unit vertical downward because it's a little bit easier. This direction is EX, this direction is EY, and the unit vector in the vertically downward direction is here. The angle that's formed, if you actually look, since the angle is beta, this angle is actually beta. And here is negative EX, just for completeness. And you can actually see if you rotate the incline back down to 0, that the gravity force would be directly in the EY direction, which makes perfect sense because there would be no inclination. So UV is equal to minus the sine of beta EX plus the cosine of beta times EY. So that tells me that the gravity force is equal to minus mg times the sine of beta EX plus mg times the cosine of beta times EY. Now we have to get the friction force. So we need the velocity of point A as viewed by an observer fixed to the piston. Well, this can be done a couple of different ways, but one way to do it is to say it's the velocity of point A as viewed by an observer fixed to the ground minus the velocity of the piston as viewed by an observer fixed to the ground. Well, the velocity of point A as viewed by an observer fixed to the ground can be computed using the no-slip condition because A is a point on the disk, on the sphere, so it's equal to the velocity of point Q plus the angular velocity of the body in the ground crossed with RA minus RQ. But we know that the velocity of Q is 0 because it rolls without slip on the ground, and we know that this angular velocity is x dot over r ez because we already got through computing it. So now we have to figure out what RA minus RQ is. Well, A is here and Q is there. So given the fact that this direction is EX and this direction is EY, we know that the position of A relative to Q is equal to minus REY minus REX. So this is minus REY minus REX, from which we can actually compute the velocity of point A. So the velocity of point A is viewed by an observer fixed to the ground. If I take this cross product, I've got EZ crossed with EY and EZ crossed with EX. EZ crossed with the R's drop out. So I get X dot times, well, I got EZ crossed with EY, which is minus EX. So this gives me EX, and then I've got EZ crossed with EX, which is EY, which gives me minus EY, right? And that's because R just drops out of the whole thing, right? So now, what's the velocity of the piston as viewed by an observer fixed to the ground? Well, that's the same as the velocity of the center of mass, and that's because the piston and point C are moving with the same velocity. So that is equal to X dot EX, which gives me that the velocity of A minus the velocity of the piston in the ground is equal to the difference between these two, which is equal to minus X dot EY. And that's equal to the velocity of point A as viewed by an observer fixed to the piston, which is what I need in the friction force. So that tells me that the friction force is minus mu times the magnitude of P times the velocity of A as viewed by an observer fixed to the piston divided by its magnitude, which is equal to minus mu times the magnitude of P times minus X dot EY, all divided by the magnitude of minus X dot EY. So because we're moving up the incline, X dot is positive, so this gives me minus mu times the magnitude of P, and then times EY, but there's a negative sign, so that flips that and becomes positive. So minus times minus, because, I'll put in parentheses, the magnitude of minus X dot EY is equal to X dot, because X dot is greater than 0. Now, P, the magnitude of P, is just equal to P. So this gives me that the friction force is equal to mu times P times EY. Notice that that tells me that the friction force is actually in, I'm going to put this in red, the friction force is actually in this direction, which makes sense because if it were in the other direction, it would pull the sphere off of the incline. So now we have everything to be able to compute the force. So the force is then equal to, what do we got here? We've got to add all these things together. We've got N plus mg plus F sub r plus P plus F sub F, which is equal to NEY, and then the gravity force is minus mg sine beta EX plus mg cosine beta EY, and then I've got plus F sub r EX plus P EX, and then plus mu times P times EY, and that has to equal mx double dot EX. So if we gather all these terms together, we've got P plus mu times P, sorry, not mu times P, we've got P plus mg cosine of beta, sorry, P minus mg sine of beta, that's in the EX direction, plus F sub r, the whole thing times EX, plus N, and then plus mg cosine of beta, and then I've got plus mu times P times EY, and that has to equal mx double dot EX, from which I get two equations. I get P minus mg times the sine of beta plus F sub r has to equal mx double dot, and I get N plus mg cosine of beta plus mu times p has to equal 0. So that's what comes out of Euler's first law. Now what we're going to do is we're going to apply Euler's second law. So the moment relative to the center of mass. So if I look at the free body diagram again, let's go back over here. You'll see that there are two forces that create a moment relative to the center of mass. They are the friction force, F sub F, and the rolling force. The friction force acts at point A, so this is equal to RA minus R bar crossed with F sub F. And then the rolling force acts at point Q, so this is RQ minus R bar crossed with F sub R. So now we've gotten through computing some of this stuff, so we'll go back when we use it now. So this is minus R EY minus R EX crossed with, we've got mu times P times EY. That's the friction force. And then we've got plus, I should put it here, plus REY crossed with F sub R EX. So if I take these cross products, I've got EX crossed with EY, which gives me minus mu times R times P times EZ. That's the first part, because EY crossed with EY is 0. And I get minus R times F sub R times EZ, which I can write as minus mu RP, and then, actually I can factor out the R as well. I might as well factor it out. So this is equal to minus R times mu P plus F sub R times little ez, because they're the same thing. And that has to equal the rate of change in the inertial frame of the angular momentum relative to the center of mass, which is equal to, because of the calculation I did earlier, it's 2/5 mr x double dot ez. And that comes from what I had computed earlier when I computed the rate of change of the angular momentum. It's right there. There's the angular momentum, and there's the rate of change, 2/5 mr x double dot ez. So now if I actually put these together, this gives me a third equation. So I have the first two equations, and then I have the third equation. The third equation looks like this. It looks like minus R times mu P plus F sub R equals 2/5 mr x double dot. So now what we can do is we can use these different equations to be able to solve for various parts. So what do we want to do? We need to get rid of things here. The easiest equation, I don't want to deal with n because n only appears in one equation. So I'm going to use 1 and 3 together. So use 1 plus 3. So the first thing we're going to do is from 3 we can solve for F sub R. And what do we get when we do that? Well, we get minus, if you divide by minus R, you get mu P plus F sub R is equal to minus 2/5 m x double dot. And so that gives you that F sub R is equal to minus 2/5 m x double dot minus mu times P. And then we can substitute that result into 1. So 1 is P minus mg sine beta. So you've got P minus mg times the sine of beta. And then what have we got here? We've got plus F sub R. But F sub R is minus 2/5 mx double dot minus mu P. Minus 2/5 mx double dot minus mu P. And that has to equal mx double dot. So this tells me that P, and then I've got minus mg times the sine of beta, and then minus mu P has to equal 7/5 mx double dot. So given that I've got a P and a mu P, this gives me 1 minus mu times P minus mg sine beta equals 7/5 mx double dot. And that is the differential equation for this particular this particular problem. This last result can be arranged a little bit. It's not really necessary to do this, but it'll make it a little bit easier just to write it as 7/5 mx double dot plus mg times the sine of beta is equal to 1 minus mu times p. That's the differential equation of motion. So now we're going to go on to another example. The next example is the following problem. I have a slender uniform arm of mass m and length L, which moves while in contact with a vertical wall, and the point of contact with the vertical wall is going to be called A. The point of contact with the ground is going to be called B. So it moves in contact with a vertical wall and the ground. The corner point here, I'm going to label it O. The center of mass of the arm, I'm going to label it C. And then this angle that's formed by the vertical downward and the arm, I'm going to call that theta. Now, let's move this over just a little bit, just so that we have a little bit more space to write everything. And gravity acts downward, and this arm has mass m and length L. Now what we're going to do is as follows, is that we are going to determine, so again, let's write this down. The objective is to determine the differential equation of motion for the arm in terms of theta, terms of the angle theta. Now, if you look here, you'll see that there's only 1 degree of freedom in this problem because a rigid body in general has 6 degrees of freedom, but we've already put this in a fixed plane, so that drops us to 3 degrees of freedom. And then there are 2 constraints, one at A, one at B, which remove 2 more degrees of freedom, so we wind up with 1 degree of freedom. So in this problem, just like we do with any rigid body mechanics problem, we have to apply Euler's laws. So I've got the force is equal to the mass times the acceleration of the center of mass, and the moment relative to the center of mass is equal to the rate of change in the ground of the angular momentum relative to the ground. I'm going to use 2 coordinate systems to solve this problem. These 2 coordinate systems are going to be as follows. The first one, I'm going to draw it actually right on this picture here because it'll just be easier to see it. The first one is going to have its origin at O. I'm going to have EX, which is going to be up along the horizontal, and then I'm going to put, let's see, well, I'll put EY up, and then EZ is going to be out of the page. Second one, I'm going to draw on the arm itself. It's going to have its origin at C. EX is going to be along CB, which is along the arm. I'm going to put EY normal to the arm such that EZ is equal to big EZ, which is out of the page. Now notice that this coordinate system, this is fixed in the body. This one is fixed in the ground. And this one right here, I'm going to call this one little e. And C together with little e is a principal axis coordinate system. So now we're ready to go. We can actually start doing calculations. So the first thing to notice is that the position of the center of mass, which is measured relative to point O, is equal to, well, let's look at it. You can see that the horizontal distance is L over 2 times the sine of theta. So it's L over 2 times the sine of theta times EX, and then plus L over 2 cosine of theta times EY. And if you don't see that, let's just draw that in red. So here is L over 2 times the sine of theta, and there's L over 2 times the cosine of theta. So this is the You can call this x, you can call this y if you want to. X is equal to L over 2 times the sine of theta. Y is equal to L over 2 times the cosine of theta. Now, let's start differentiating. So the velocity of the center of mass. Now this can be just a straight differentiation because Ex and Ey are fixed in the inertial frame. So this gives you L over 2 times theta dot, don't need the parentheses yet, theta dot cosine theta times Ex, and then minus L over 2 theta dot times the sine of theta times Ey. This is, now if we differentiate this again, we get L over 2 times theta double dot cosine of theta minus theta dot squared times the sine of theta times Ex, and then we get minus L over 2 theta double dot times the sine of theta plus theta dot squared cosine of theta times Ey. So that's the acceleration of the center of mass. Next, we need the angular momentum. The angular momentum relative to the center of mass is equal to the inertia tensor of the body multiplied by the angular velocity of the body in the ground. And again, because this basis E is a principal axis basis, principal axis coordinate system, if we include C, we get Ix bar, Iy bar, Iz bar, and all zeros. Similarly, the angular velocity of the body in the ground, when expressed in this basis E, is equal to 0, 0, theta dot. So that tells us that the angular momentum relative to the center of mass, when you multiply these together, gives me Iz bar theta dot Ez. But for a slender uniform arm, Iz is equal to ml squared over 12 theta dot times Ez. So now I can compute the rate of change of the angular momentum relative to the center of mass. That's equal to ml squared over 12 theta double dot Ez, because Iz is inertially fixed, so there's no second term in the transport theorem. So now we've computed everything on the right-hand side. Now we need to draw the free body diagram and do the kinetics. So if I draw the free body diagram, what have we got? Well, we have this arm. What are the forces acting on this arm? Well, the forces acting on this arm are, there's a force N sub x, there's a force N sub y, then there's a force mg. And that's it. So now we can actually write these forces out. N sub x actually is in the Ex direction, it's horizontal. N sub y is vertical, it's in the Ey direction. And then mg is also in the Ey direction, but it's in the negative Ey direction because I put Ey up. So now we can first write Euler's first law. The force is equal to N sub x plus N sub y plus mg, which is equal to N sub x Ex plus N sub y Ey minus mg Ey. And that is equal to N sub x Ex and then plus N sub y minus mg Ey, and that has to equal the mass times the acceleration of the center of mass. So from this, we get that N sub x Ex plus N sub y minus mg Ey has to equal m, and now let's go back to this acceleration of the center of mass. We get ml over 2 times, what do we got? Theta double dot cosine theta minus theta dot squared sine theta. And that's times Ex. And then we have minus ml over 2 times theta double dot sine theta plus theta dot squared cosine theta. Theta double dot sine theta plus theta dot squared cosine theta times Ey. So from this you get two equations. first equation you get is n sub x is equal to ml over 2 times theta double dot cosine theta minus theta dot squared sine of theta. Second equation you get is n sub y minus mg is equal to minus ml over 2 theta double dot sine theta plus theta dot squared cosine of theta. Now you'll see that neither one of these is going to produce a differential equation because they're two unknown reaction forces. So next what we have to do is we have to compute the moment relative to the center of mass so that we can equate it to the rate of change of the angular momentum. So you look here, you'll see there are two forces that create a moment relative to the center of mass, n sub x and n sub y. N sub x acts at point A, so this is equal to Ra minus R bar crossed with n sub x plus, and then the second one acts at point B, and it creates a moment due to the force n sub y. Now Ra minus R bar, because of the directions I labeled here, if you look, Ex is along CB. So the position of A relative to the center of mass is minus L over 2 little ex crossed with n sub x big Ex. And then L over 2 little ex crossed with n sub y big Ey. So now we have to actually compute these, but first let's put these together. So you get minus L n sub x over 2 Ex crossed with big Ex plus L n sub y over 2 little ex crossed with Ey. So if you now look at these equations, at the bases, so when you put these back, you actually, if you look back at the way I define the coordinate systems, you can actually see that Ex is this way, Ey is this way, little Ey is this way, and little Ex is that way. And the angle here, this angle is theta, which makes that angle theta. So as a result, we can write it either way, but it's easiest in this case. We only need little ex. So little ex is equal to, well, it's equal to sine of theta times big Ex minus the cosine of theta times big Ey. So you can see here that as a result of this, we can now compute Ex crossed with big Ex. That's equal to Ex crossed with big Ex. We get cosine of theta times Ez, which is also equal to cosine of theta times little ez. The next one we need is Ex crossed with Ey. This is equal to, well, if I take Ex crossed with Ey, I get sine of theta times big Ez, which is equal to the sine of theta times little ez. So from this, I can actually get this equation now, which tells me that the moment relative to the center of mass is then equal to minus L n sub x over 2, and then times Ex crossed with big Ex, which is cosine of theta. I'm going to put the ez when I'm all done. And then I've got plus L n sub y over 2, and then plus L n sub y over 2 times the sine of theta, and this whole thing is multiplied by Ez, and that has to equal the rate of change in the inertial frame of the angular momentum relative to the center of mass. So as a result of that, we get minus L n sub x over 2 times the cosine of theta plus L n sub y over 2 times the sine of theta times Ez is equal to ml squared over 12 theta double dot Ez, from which we get the third equation, which gives us L over 2 times n minus n sub x cosine theta plus n sub y times the sine of theta is equal to ml squared over 12 theta double dot. So now we have a way of being able to eliminate the unknowns. So if you look at the previous two equations, you'll see I had these two. So what you can actually do is from 3, now you can actually simplify and you can get the following. You get n sub y times the sine of theta minus n sub x times the cosine of theta is equal to ml over 6 theta double dot. So now what we can do is we can take 1 and 2. So look at what happens. If you multiply 1 by, well, let's look at 1. If I multiply 1 by, because there's an n sub x here, by cosine theta, what do you get? You get n sub x times the cosine of theta is equal to ml over 2 times theta double dot cosine theta minus theta dot squared times the sine of theta. And then if you add mg to 3, so if you add mg to 2 and multiply by the sine of theta, what do you get? Well, if you look over here, you're going to get n sub y times the sine of theta is going to equal mg sine of theta, and then you get minus ml over 2 times theta double dot sine theta plus theta dot squared cosine of theta. Now what you can do is you can subtract the second to last result from the last result. And actually, I'm sorry, I made a mistake up here. This is no, there's no mistake there. Sorry. These two results. This one, looking at the wrong result. This one and this one. So subtract the second to last result from the last result. What do you get? You get n sub y times the sine of theta minus n sub x times the cosine of theta is equal to, you get mg times the sine of theta. Now look what winds up happening when you actually do this. Actually, I've got to multiply here by sine of theta. I forgot the sine of theta. And here I've got to multiply by cosine of theta. Okay, now if you subtract, what winds up happening? You've got ml over 2 theta double dot cosine theta sine theta in the second to last expression. And then if you notice, you've got ml over 2 theta double dot, cosine squared theta. So this gives you, if I take the first term in the second to last expression and the first term in the parentheses in the last expression, this gives me minus ml over 2 theta double dot sine squared theta minus ml over 2 theta double dot cosine squared theta, which just gives me minus ml over 2 theta double dot. Then what I do is I got minus ml over 2 theta dot squared cosine theta sine theta, and then I get plus ml over 2 theta dot squared sine theta cosine theta, so they all drop out to 0, and I'm left with what's sitting here. If you want to see it another way, let's actually write these out just so that we can be a little clearer with all this. I've got n sub y times the sine of theta is equal to mg times the sine of theta. Now let's multiply all this out. We've got minus ml over 2 theta double dot times sine squared theta. And then we have minus ml over 2 theta dot squared, and then we've got cosine theta sine theta. And then we have n sub x cosine theta is equal to, well, if we line everything up, we've got ml over 2 theta double dot cosine squared theta. And then we've got plus ml over 2 theta dot squared cosine theta sine theta. But there's a negative sign there, so this actually becomes negative. So now let's subtract. what happens. You get n sub y sine theta minus n sub x cosine theta is equal to mg times the sine of theta. And now look what winds up happening. You get you've got ml over 2. You got cosine squared theta plus sine squared theta, which just gives you 1. And so this is actually a plus sign right here. Let's see here. So minus. No, sorry. This is a minus. The minus sign was correct. So the minus sign is correct here. And then, as we're just subtracting in the order in which we see it. So we got sine squared theta plus cosine squared theta is 1. And if you notice that the other two terms wind up canceling out. Now this quantity right here, I had already solved for in this expression, which is ml over 6 theta double dot. So this gives me ml over 6 theta double dot is equal to mg sine theta minus ml over 2 theta double dot. Now, I've got ml over 6 and ml over 2. ml over 2 is 3 ml over 6. So if I add 3 ml over 6 to ml over 6, I get 4 ml over 6. So you get 4 ml over 6 theta double dot is equal to mg times the sine of theta. If you then drop it, you get 2/3 ml theta double dot is equal to mg sine theta, which also gives you theta double dot is equal to 3/2 g over L times the sine of theta. And that's the differential equation of motion. Okay, so the last example that we're going to do in this video is the following problem. I have a sphere of mass m and radius r which rolls without slip on the ground, and at a height h down the center of the sphere, center vertically on the sphere, there's a force P that's being applied. So this force is being applied at a height h above the ground. The center of the sphere I'm going to denote as point C, and the radius of the sphere is r, and I'm going to denote the displacement of C relative to the ground by displacement x, and then I'm going to call this point here Q, and there's no slip here. And the objective is to determine the differential equation. Determine the differential equation of motion in terms of x. Okay. Now once again, we're going to do this with Euler's laws. So we know that the force is equal to the mass times the acceleration of the center of mass. We know that the moment relative to the center of mass is equal to the rate of change in the ground of the angular momentum as viewed by an observer fixed to the ground. In this case, I'm going to have two coordinate systems. I'm going to have one, which is going to have its origin at c when x equals 0, and it's going to have ex to the right. I'm going to put ey down, and then ez into the page. This is fixed in the ground. I'm going to put another coordinate system which is going to be fixed to the body. It's going to have ex, ey, and ez defined such that ex is along this radial line, ez is into the page, and ey is the cross product. This is fixed in the body. Now, and its origin is at C. So now, we know that the position of point C relative to where C is when x equals 0 is equal to x ex, from which we get, and this is also equal to the position of the center of mass. The velocity of the center of mass is then equal to x dot ex, and the acceleration of the center of mass is equal to x double dot ex. Next, we need the angular momentum relative to the center of mass, which is equal to the inertia tensor of the body multiplied by the angular velocity of the body and the ground. But note, I did not give you an angle in this problem. So we have to figure out what this angular velocity is in terms of x. So the way we do that is we use the no-slip condition. The no-slip condition says the velocity of point Q on the body in the ground has to equal the velocity of point Q on the ground in the ground, but that is equal to 0, which makes this equal to 0. So now we know that the velocity of point C is equal to the velocity of point Q plus the angular velocity of the body crossed with RC minus RQ. But the velocity of Q is 0, and this is omega EZ crossed with minus R E Y. Actually, I called it little r in this case, so let's be consistent with what I called it. So this is equal to R omega EX, but that is equal to X dot EX, which says that R omega is equal to X dot, which says that omega is equal to X dot over R. So now we can go back and we can figure out this angular momentum. So we know that the inertia tensor of the body, when expressed in this basis E, which I'll call this E, since it's a principal axis coordinate system, is Ix bar, Iy bar, Iz bar, and all zeros. The angular velocity of the body in the ground, when expressed in this basis E, is equal to 0, 0, omega, but I know that omega is equal to x dot over r. So this tells me the angular momentum is equal to Iz bar times omega Ez. Iz bar is equal to 2/5 for a sphere is 2/5 mr squared times omega Ez, but omega is equal to x dot over r, so this is 2/5 mr squared times x dot over r Ez, and that gives 2/5 mr x dot Ez, which gives that the rate of change of the angular momentum is equal to 2/5 mr x double dot Ez. So now we have everything on the right hand side. So now we have to figure out, to draw the free body diagram, figure out what's going on with the rest of this. And you can see that there's a force which I call P, underbar here, P, and here is the free body diagram. Okay, here's the force P. There's a rolling force, which is also a static friction force. There's a normal force, and then there's a force of gravity. Now let's look. You'll see that this force acts at a point which I'm going to call A. All right? So in order to be able to compute the moment, the resultant force first and then the moment. So the resultant force, we know that the force is equal to P plus F sub F plus N plus mg. So let's figure all these out. Well, P is in the EX direction. F sub F is also in the EX direction, and it's unknown. And we know that N is in the EY direction, and we also know that mg is in the EY direction, because I put EY in this case, I put EY down. So that tells me that the force is equal to, if I add all these up and I put all the components together, I've got P plus F sub F times EX, and I've got plus N plus mg times EY, and that has to equal mx double dot EX. x, because that's equal to the mass times the acceleration of the center of mass as viewed by an observer in the inertial frame. So I get two equations from this. I get P plus F sub F is equal to mx double dot, and I get N plus mg is equal to 0. Next, I need to compute the moment relative to the center of mass. Now this is a little bit trickier because there are two forces that create a moment. The first one is, because I labeled the point at which P acts, it's RA minus R, I labeled it A. So it's RA minus R bar crossed with P, and then I get plus RQ minus R bar crossed with F sub F. Now we got to figure out these. So let's look at RA minus R bar. Well, if I look at this picture, you can actually see, I'm going to draw this in red. This distance, because this whole distance from here to there, that distance, that's h, which makes this h minus r. Now this distance here completes a right triangle. You can actually see this right triangle. This is r. And so let's call this b. All right? So given that I called it b, you can see that r squared has to equal, and there's no underbar on b, it's just b. So if I look at this from using the Pythagorean theorem, you'll see that r squared is equal to b squared plus h minus r squared. That's all I really need to know. I mean, so b is actually equal to r squared minus h minus r squared, the whole thing raised to the 1/2. But I don't really need to worry about that. I'm just going to leave it in terms of b, and then any algebra that we need to do, we'll deal with later. But I know the following. You can see that the position of A relative to the center of mass is equal to minus h minus r ey minus b ex. So this is equal to minus h minus r ey and then minus b ex. So now what I can do, and of course, well, rq minus r bar, this is the somewhat easier one. This is equal to plus r ey, because I defined ey to be downward. So this gives me that the moment relative to the center of mass is equal to minus h minus r ey minus b ex crossed with p ex, and then plus r ey crossed with f sub f ex, which is equal to, well, ey crossed with ex is minus ez, so I get h minus r times p times ez. Notice I didn't even need to worry about the b. It didn't even come up. And then minus r times f sub f ez, which is equal to h minus r times p minus r times f sub f times ez. Okay, so that's the moment. Now what does that moment have to equal? The moment equals the rate of change of the angular momentum, which is equal to 2/5 mr x double dot ez, where I'm using the angular momentum from earlier, 2/5 mr x double dot ez. So that tells me that h minus r times p minus r times f sub f has to equal 2/5 mr x double dot. So that is the third equation. So I'll erase this and I'll label this 3. Okay? So now what we get is we can actually solve these. We can actually figure out from 1 we can actually solve for f sub f. So from 1 solve for f sub f. What do we get? We get f sub f is equal to, we get mx double dot minus p. Right? Now substitute that. So substitute f sub f into 3. What do we get? We get h minus r times p minus r times mx double dot minus p is equal to 2/5 mr x double dot, which gives h minus r times p minus mr x double dot plus r times p equals 2/5 mr x double dot, which gives we can add mrx double dot to both sides. We get h minus r times p plus r times p equals 7/5 mr x double dot. And you can see there's a minus rp plus rp, which cancel out, which gives h times p equals 7/5 mr x double dot. And we can actually rearrange this again if you want to, and we can actually just solve for x double dot. So then x double dot is equal to, well, we get 5hp all divided by 7mr. And that's the differential equation, where p is the force that's being applied at that point that I said up at the top, a distance h, a height h above the ground. So we've now done 4 problems in complete detail using Euler's laws, and in the future we'll study more problems. But for this video, this is enough, and so hopefully these problems will carry you a reasonable ways into furthering your understanding of kinetics of a rigid body.